Next up in geometry, we're going to be looking at trigonometry. And first we're going to look at the different trig ratios. You see that we have two different triangles, ABC and RST, and those two triangles are similar to each other. We can tell that because of angle-angle similarity. And since those triangles are similar to each other, we can say that corresponding sides AB over RS is in the same ratio as AC divided by RT. Now if you cross multiply, we get this product. And then if you divide both sides by AC and RT, we get this equation. In other words, the length of AB divided by AC is in the same proportion as RS divided by RT. That is our first trig ratio. Trig is the ratio of sides and angles based on right triangles. First one we have is the sine ratio. This little symbol right here is called theta. It stands for that angle. It's a Greek letter. From this angle we have the opposite side, the one that's not touching it. We have the hypotenuse, which is obviously opposite the right angle, and then the other adjacent side that's not the hypotenuse, we just call the adjacent. And the sine ratio is opposite length divided by hypotenuse length. So sine is opposite over hypotenuse. The next trig function we have is cosine. Cosine is adjacent length divided by hypotenuse length. So cosine is adjacent over hypotenuse. Then our third one is tangent. Tangent is the opposite length divided by the adjacent length. So tangent is OA. If you want to remember what those different trig function ratios are, it's SOHCAHTOA. So going back up to this problem, the sine of angle theta is this AB divided by AC, and the sine of this angle theta is RS divided by RT, and it'll give you the same thing because those angles are equal. So first example, use the definitions to find the following. We want to find the sine of A. From angle A, 13 is considered our hypotenuse, 12 is considered the opposite, and 5 is considered the adjacent. We're going to put down our reminder for what the trig ratios are. The sine of angle A is the opposite divided by the hypotenuse, which would be 12 over 13. The cosine of A is the adjacent over the hypotenuse, so that's going to be 5 over 13. And lastly, the tangent is opposite over adjacent, which is going to be 12 over 5. None of these fractions can be simplified at all, so we're just going to leave them in that exact form. Next up, we're supposed to find the sine, cosine, and tangent of angle B. Now, relative to angle B, the opposite is now 5. The adjacent is going to become 12, so the opposite and adjacent changed because of the location of our primary angle, but the hypotenuse is still 13. So the sine of angle B is the opposite of 5 divided by the hypotenuse of 13. The cosine is our adjacent of 12 divided by our hypotenuse of 13. And tangent is the opposite of 5 divided by the adjacent of 12. Now there are some relationships that we can look at here. First of all, the relationship between angle A and angle B. Because they're the two acute angles in a right triangle, that means that A and B are complementary to each other. And then if you look across the columns, the sine of angle A is the same as the cosine of angle B, because what was the opposite for angle A is the adjacent for angle B. Another one that you might see is that cosine of A is equal to the sine of B. Those are the same as well. And then the final one that we're going to look at is that the tangent of angle A is the reciprocal of the tangent of B. Notice there's a relationship between the sines and cosines that we looked at. The sine of an angle is equal to the cosine of its complement. And there is a relationship between the tangents of angle A and angle B that can be summarized in the statement. The tangent of an angle is the reciprocal of the tangent of its complement, which is what we were just looking at up above. Example, find the exact value of the indicated ratios. First of all, we want to know, what is this talking about? This is another variable. It's not A and B this time. This is the Greek letter alpha. This is the Greek letter beta. So the sine of alpha is the opposite divided by the hypotenuse. The opposite is 15. The hypotenuse is 27. And that is going to simplify. I can divide both of those by 3 and get 5/9. And really, at the very beginning, I could simplify those because I'm going to be simplifying them at some point anyways. The next part asks for the cosine of alpha. I want to know what is my adjacent length divided by the hypotenuse. Problem is I don't know the adjacent yet, but it is a right triangle, which means Pythagorean theorem works. I'll call this x for right now. So 5 squared plus x squared equals 9 squared. X squared equals 81 minus 25. X squared equals 56. And we can simplify that down to 2 root 14. So we're going to say that x, this adjacent, is equal to 2 root 14. Now in actuality, it would be 6 root 14 because we divided those sides by 3 already, which means this side was divided by 3. So to get back to the original, it would have been 6 root 14, but we'll keep using that number for the sake of easier arithmetic. So the cosine is our adjacent divided by our hypotenuse, and lastly the tangent is the opposite divided by the adjacent. And then if we rationalize that, we get 5 root 14 over 28. Sine of b, from what we looked at before, I know that the sine of b is equal to the cosine of alpha. So this is 2 root 14 over 9. The cosine of b is the same thing as the sine of alpha, so that's 5/9. And the tangent of beta is the reciprocal of the tangent of alpha, so it's 2 root 14 over 5. Taking the reciprocal of the original, because then I don't have to worry about trying to rationalize the denominator. If you want to go through what is the opposite, adjacent, and hypotenuse for angle beta, you can do that, but this is a little shorter way to find those. Next, we're going to actually solve a right triangle. We have 3 things that we're going to use, either the Pythagorean theorem, complementary angles, or the trig ratios. Here's our first example. We have angles A, B, and C. And then the sides are segment AB. We're actually going to call that one little c. Whatever angle we have, opposite of that is the side little c. If this is angle A, then that means we're going to call this segment down here little a. And then we also have little b, which would be segment capital AC. We know from the given that little c is 14. We know that angle B is 41 degrees, and we know angle C is 90 degrees. Those things are given to us over here in the original problem. I don't know capital A, I don't know little a, I don't know little b. First I'm going to find capital A. Capital A is complementary with the 41 degree angle, so capital A is 49 degrees, and it is exactly that, so I can put the equal sign. Next, to find little a, I could say that the sine of angle B is equal to the opposite divided by the hypotenuse. Sine of B is this length, which is little b, divided by the hypotenuse, which is 14. And I know that angle B is 41 degrees, so that means that I can substitute 41 degrees in for B. Now this is an algebraic equation, which means that I can perform a regular algebra on it to get little b by itself. I'm going to multiply both sides by 14, which leaves me with an exact value for b of 14 times the sine of 41 degrees. And if you use your calculator to evaluate that, that gives you an approximate value of 9.18. Next up, to find little a, well, we have this 41 degree angle. Little a is down here. This is the side that I want to know. I know that the exact value of the hypotenuse is 14. So from the 41 degree angle, A is our adjacent, 14 is our hypotenuse. We know this one. We want to know that one. The trig ratio that uses adjacent and hypotenuse is cosine. So the cosine of angle B of that 41 degree angle is equal to our adjacent divided by our hypotenuse of 14. Once again, we can use algebra to solve this. So multiply both sides by 14. 14 times the cosine of 41 degrees is equal to little a. Now if you use your, you should get a value for a of approximately 10.57. And one thing to check before you move on, largest angle should be opposite largest side, smallest angle opposite the smallest side. So here is this triangle solved. Next one. We have angle X, angle Y, angle Z, little x, little y, and little z. We know that capital Z is 90 degrees. We know that little z is equal to 42 and little x is equal to 13. We need to find capital X, capital Y, and little y. To find little y, we can use Pythagorean Theorem. So we have 13 squared plus y squared equals 42 squared. And when you solve that, you get an approximate value for y of 39.94. Next, we're going to find an angle. From angle y, 13 is the adjacent, 42 is the hypotenuse. The trig function that uses a and h is cosine, so we would say that the cosine of angle y is our adjacent divided by the hypotenuse. To get angle y by itself, we take the cosine inverse of both sides. And what that does for us is it makes the left side simplify down to angle y all by itself. The right side is cosine inverse of 13 over 42. So on your calculator, you're going to hit second cosine, 13 divided by 42, and that gives you an approximate angle measurement of 72.0 degrees. We'll back up, and the last thing we have to find is x. Now, angle y is a rounded number, so we don't want to use 72.0. However, in the calculator, it's reading as 71.969 and so forth. And since x and y are complementary angles of each other, we can go back to the calculator and do 90 minus answer. And this gives us an approximate answer of 18.0 degrees, which looks like we just used the 72.0. However, in your calculator, we have 18.0305 and so forth. That is an exact number that we could use if we needed future calculations. We could have it stored in the calculator. These are our answers. This is the solution for that particular triangle. And here is one last problem that you can choose to solve or move on if you like to another right triangle, triangle RST. You're given lengths of 11 and 14, and similar to the other ones, you can use Pythagorean Theorem, you can use trig, or you can use those trig inverses, which is what we just used to find that angle.